Yeah, let's talk about Ferrari's method for quartic equations. Don't forget, the degree of polynomials are decided by the biggest exponent of the variable. And if the biggest exponent is one, you have a linear equation. If it's two, you have quadratic. If it's three, you have cubic. And if it is four, you have quartic. And previously, we've seen different methods of solving different kinds of polynomial equations, starting with factorization of different types, and then, um, you know, and that we have the quadratic equation and things like that. Then we saw Cardano's method for cubic equations previously. So right now, our attention shifts to Ferrari's method for quartic equations. That's equations of degree 4, polynomial equations of degree 4. So let's look at that. By the end of this lesson, you should be able to recognize the general quartic equation, which looks like ax raised to power 4 plus bx raised to power 3 plus cx squared plus dx plus e equals 0. Take note that A and E are usually very important. A is the leading coefficient, E is the constant, and then 4, I mean, that 4 is important. That tells us it's quartic in the first place. So once you recognize it, then you can convert it to a depressed quartic, y raised to power 4 plus py squared plus qy plus r equals 0. Now, just like we saw in the Cardano's method situation, depressing a cubic equation removes the second order, the variable in power 2. So if you depress a quartic equation, on the other hand, you remove the expression, the variable in order 3, right? So recognize the equation, you convert it to depressed quartic, and you form the resolvent cubic of Ferrari's method. So you then understand how solving the resolvent cubic lets you factor the quartic into two quadratics. So apply the method or its simplified variant to solve concrete quartic equations. Now, for the most part, I may not really go in depth about this. Okay, let's see. I want to see how far I want to go, because it can be really tedious. Because I'm sure that for almost any equation, you can use Ferrari's method for. You can actually do the regular, you know, you can do the regular factorization and the factorizing difference of two squares, sum of two squares, and things like that, and you still find your way around. So I'm just introducing this as a possibility. So in case you need maybe you have tried other methods for a particular equation and you don't get it, you can then consider the Ferrari's method for a quartic equation in particular. So the general quartic and depressed quartic, for instance, we start with the general quartic equation x raised to power 4 plus bx cubed plus cx squared plus dx plus e equals 0. Now, this is the general one because in this case now, the leading coefficient is 1, right? So that way it is now a monic quartic equation. So you don't have so we because even if you had a coefficient that you want to, you would have divided through by whatever was there. So, and you see that here now, but if you divide this original expression through by a now, that's why b over a now becomes this b over a now becomes b. C now is c over a, d is d over a, and e is e over a. That's big. All the big B, C, D, and E, they are those corresponding alphabets over A. So if you first divide by A to make the equation monic, this is what we have now. So Ferrari's method begins by removing the x cubed term. So to use the Ferrari method, just like we removed x squared for Cardano, we now remove x cubed for Ferrari. So Ferrari's method begins by removing the x cubed term. So we substitute x equals y minus b over 4. In the case of Cardano, we substituted y minus b over 3. Yeah, as you can, if you remember. So after expanding and simplifying, the equation becomes, so what we are saying is that once you make it into a monic quartic equation like this, you now substitute y minus b over 4. So you have y minus b over 4 raised by 4, y minus b over 4 raised by 3, y minus b over 4 raised by 2, y minus b over 4 here. So by the time you expand, do all of that, tidy up and everything, after expanding and simplifying the equation, it becomes y raised by 4 plus py squared, right? Plus qy plus r equals 0. So you now have it in the form of a quartic equation that does not have a cubic term. So this is now called the depressed quartic because no y cube term. Now, this thing that you have just in two lines, if I really want to do it, you can already imagine this is power 4. So I have to use Taylor's theorem. I have to use Taylor's, yeah, I have to use, what is that thing called now? Things like Pascal's triangle to get coefficients and everything. But long and short, by the time you simplify, you end up having something like this. And of course, you can already imagine that P, Q, and R are things in terms of B over 4, B and all of that, right? So once you do that, you get a depressed quartic, and then we go ahead and talk about formulas for PQ and R, for the monic case now. So like I said, PQ and R are not just like that. So the formulas for PQ and R in the monic case, x raised to power 4 plus bx cubed plus cx squared plus dx plus z equals 0. After substitution, after substituting x equals y minus b over 4, the coefficient PQ and R in y raised to power 4 plus py squared plus qy plus r is 0. Okay. Then P, that is C minus C 3B squared over 8. Then Q, D minus BC over 2 plus B cube over 8. R is E minus BD over 4 plus B squared C over 16 minus 3B 4 over 256. So in essence, you can actually, once you know these substitutions, you can actually substitute your values because we already know B, C, D, and E. You can just put them up here and you can get P, Q, and R. And you fix it up here and you get your quartic equation. So the Ferrari first step is always to compute P, Q, and R. So using these expressions right here. So talking about the Ferrari's idea, right? So we can think of difference of two squares, right? So Ferrari's key idea is to turn the depressed quartic y raised to power 4 plus py squared plus qy plus r into a difference of squares. So you have y raised to power 4 plus py squared minus qy plus r, and you now turn it into quadratic in y squared minus linear in y squared. So with this one now, you can now do it as difference of two squares. So more concretely, one can show that there exists a parameter z such that y raised to power 4 plus py squared plus qy plus r is the same thing as y squared plus p over 2 plus z, all squared minus 2zy plus q over 2z raised to power 2. So we want to be able to do that, okay? So provided Z satisfies a certain cubic equation called the resolvent cubic. Once we have a difference of squares, we can then factor a squared minus b squared to be a minus b into a plus b, which we have seen, we've all encountered a lot of times. So the quartic becomes a product of two quadratics in Y, right? So let's talk about the resolvent cubic. The resolvent cubic. So to make the identity in the previous cell valid, the parameter z must satisfy the resolvent cubic, which is 8z cubed plus 4pz squared plus 2pz minus q squared equals 0. So z must satisfy uh, this. Okay, the summary of the logic is that you start with the depressed quartic y raised to power 4 plus py squared plus qy plus r, try to rewrite it in a special square minus square form depending on z, then enforcing exact equality leads directly to the cubic equation above. So this equation now is to enforce exact equality. Solving this resolvent cubic gives a value of values of z that allow the quartic to factor into two quadratics. Okay. And I know we've done this, we did this under the general, what is that, an FTA, foundational theorem of algebra, where we saw that if you are willing to look into the complex plane, and of course, if you want to take care of multiplicities, every equation can be factored into exactly the number of its degree, right? So if you are considering both real and complex or just complex, if you are considering everything, you can factor every polynomial into the number of its degree, so to speak. So once you have a real root z of 8z squared plus 4pz squared plus 2pz minus q squared equals 0, the depressed quartic can be rewritten as y raised to power 4 plus py squared plus qy plus r equals y squared plus p over 2 plus z raised to power 2 minus 2zy plus q over 2z squared. Then you apply the identity that you have a squared minus b squared. That's a minus b into a plus b, with a now being y squared plus pb over 2 plus z, and b is 2zy plus q over 2z. So this yields two quadratic equations in a minus b equals 0 and a plus b equals 0. So each is a quadratic in y, solvable using the quadratic formula. Finally, you can undo the substitution x equals y minus b over 4 to obtain the solutions of x. So after you have got your after taking care of this now, you can always get back your, these ones are in terms of z, right? So you can always get your x back. Okay. So let's look at algorithm cheat sheet for uh, a monic quartic equation. So Ferrari's method cheat sheet. So for x raised to power 4 plus bx cubed plus cx squared plus dx plus z equals 0, first depress the quartic by substituting x equals y minus b over 4. That's what I've been saying all along. Okay. So that there you obtain y raised to power 4 plus py squared plus qy plus r equals 0. I mean, we can do that. Just put y minus b raised to power 4 raised to power 4. Y minus b over 4 raised to power 4. Expand. b into y minus y, b into y minus b over 4 raised power 3, expand, c into y minus b over 4 raised power 2, expand, then you have d into y minus b over 4, and e equals 0. So by the time you tidy it up, you obtain y raised power 4 plus by squared plus qy plus r equals 0. So you'd have depressed the quartic like that by making the substitution. So the cubic term is gone. Then step 2, you form the resolvent cubic, which is something like 8z cubed plus 4pz squared plus 2pz minus q squared equals 0. So then you then solve the resolvent cubic, find at least one real root z. So we write as a difference of two squares like what you have here like this. Then you now have factor into quadratics, that's a squared minus b squared, that's a minus b into a plus b equals 0. So this produces two quadratic equations in y. Then 6 now, you then solve the quadratics, that solve both quadratics for y. Then 7 back substitute. So you have x equals y minus b over 4. So this gives the 4 root, possibly repeated, of the original quartic. Okay? Now, look at the visual flowchart for these things you have said. So this is the whole of it. But it's the same thing I've been saying. So start with the quartic. You have x raised to power 4 plus bx cubed plus cx squared plus dx plus z equals 0. Then depress the quartic by substituting x equals y minus b over 4. And you get y raised to power 4 plus by squared plus qy plus r equals 0. Then form the resolvent cubic where you have z cubed for 4 plus 4pz squared plus 2pz minus q squared equals 0. Then equation in z now. Then you can then solve the resolvent cubic, find a real root z. Then difference of squares now. You do difference of squares and then factor into quadratics. So you have two quadratic equations in y. Then solve the quadratics now. So solve the quadratics, solve both quadratics for y. Then back substitute x equals y minus b over 4. Then you collect the four roots of the quartic. And that ends the process. So worked example now. So if you have an already depressed case where q is equal to 0, so so in this case now solve the quartic x raised to power 4 minus 10x squared plus 9 equals 0 using the framework of Ferrari's method. So this is already depressed, so you don't worry yourself about depressing, about substituting x equals y minus b over 4. So this is already depressed quartic, no x cubed term. So we can view it as y raised to power 4 plus py squared plus qy plus r equals 0. And if you look at it, p is minus 10, q, there's no term in x, right? So q is just 0, and there's a constant which is r, which is 9. So, and in this case, we just know that y is equal to x because b is equal to 0. Okay. So now we can then do, for example, one, we have the resolvent cubic for the framework. So the resolvent cubic is usually 8z cubed plus 4pz squared plus 2pz minus q squared equals 0. So if you substitute p equals minus 10 and q is equal to 0, that means you have 8z cubed plus 4 into p is minus 10z squared plus 2p, p is minus 10. So you have 2 into minus 10, z minus 0. So you have 8z cubed minus 40z squared minus 20z equals 0. Then you can factor this now. So if, of course, to solve any problem like this, the first thing you want to think about is factoring. So we can factor this like we've seen. So 4z is common. So you have 4z into 2z squared minus 10z minus 5 equals 0. So you have this is a quadratic expression. So the possible z values are, you have 4z equals 0, so z can be 0, or 2z squared minus 10z minus 5 is 0. So for actual computation, this is messy and not necessary because q is equal to 0. So Ferrari's full machinery is more useful when q is not equal to 0. So this q, because q is 0 now, it's not necessary. But when q is not 0, then it's fine. So in this special case, we can solve the quartic more simply. Okay. So the quartic expression, like from what you have here, I mean, I can easily make this into a difference of two squares and solve. Like I said, that's why I'm not taking too much time to worry about this quartic thing, because even the way it is now, I can do that idea of, forming it into a perfect square, and then I have another pattern. I can have difference of two squares, and then I get my result. But I mean, it's important that you understand that there's something like a quadrat, like Ferrari's method. So solve as a quadratic in x squared, for instance. So since q is equal to 0, and we said there's no point, so you can see that in this depressed form, we already did something about everything is in x is in terms of x can be said to be in terms of x squared. So you can simply just do that, which we've done a couple of times. So you just square it. You have x squared squared minus 10 into x squared plus 9 equals 0. So let u be x squared, and you have u squared minus 10u plus 9 equals 0. Then you can solve u. So you have a is 1, b is minus 10, c is 9. So you have minus b, that's minus 10, that's plus 10, plus or minus square root of minus b squared, that's minus 10 squared, that's 100, minus 4 times a times c, that's 4 times 1 times 1, that's minus 36 over 2. So you have 100 plus or minus square root of 64 over 2, that's 10 plus or minus 8 over 2. So you have u is 10 plus 8 over 2, that's 18 over 2, which is 9. Or u is 10 minus 8, 2 divided by 2, that's 2. So u is either 9 or 2 or 1. Thus, you know that x squared is 9 or x squared is 1. So hence the roots are simply x equals plus or minus 3 if you take the square root of both sides, or x is plus or minus 1. So with this now, you have your 4 results easily. Okay, so this example shows the special case where q is 0 and the quartic is easily reducible to a quadratic in x squared. So Ferrari's general framework still applies, but a simpler approach is available. So before you would need Ferrari's method, it will be it's difficult. I mean, there's hardly it would be rare for you to find a case that really requires Ferrari's method because it's really tedious, but you can always find a simple way to solve most problems. So if you cannot find a simple way, then you cannot think of Ferrari's method. Now let's look at the general case setup where q is not equal to 0. So example 2 for the setup now. So consider the quartic with distinct roots minus 3, minus 2, 1, and 4. So that's like x plus 3 into x plus 2 into x minus 1 into x minus 4 equals 0. Expanding gives x raised to power 4 minus 15x squared minus 10x plus 24. So, I mean, even if you saw this, the first thing you are thinking of should not be Ferrari. You are thinking of how to factorize, how to see the possible roots. And you know you can get the possible roots by breaking down. Okay, so this one is so the leading coefficient is 1 already because it is in the standard form, and this is 24. So the possible root should be something like plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, and plus or minus 12, plus or minus 24. So these are possible roots you can find there. So you can see 1, 2, 3, 4 are roots here, plus or whether plus or minus. So here now, in this case now, b is equal to 0, you know, because there's no x cube. It is already depressed. And c is minus 15. So once b is 0, it is already depressed because the standard form is x raised to power 4 plus big B x cube plus big C x squared plus big D x plus E plus big E rather. So it means big B is not available because there's no x cube. And big C is minus 15. Big D is minus 10. Big E is 24, as you can see. So the equation is already monic with no x cube term, and we can take y to be x straight up. Then the depressed equation, the depressed quartic is y raised to power 4 plus py squared plus qy plus r equals 0, with p equals minus 15 and q is minus 10 and r is 24. So because q is not equal to 0 now, we can easily form the we can form the resolvent cubic. Okay, so we use the resolvent cubic formula, which is 8z cubed plus 4p squared plus 2pz minus q squared equals 0. So substitute p is minus 15 and q is minus 10, like we already obtained up there. Okay, so we have p is minus 15, q is minus 10. So you have 8z cubed plus 4, p is 15, you have z squared plus 2, p is minus 15, z minus q squared, that's minus 10 squared. So you have 8z squared minus 60z squared minus 30z minus 100 equals 0. So you can divide by 2 to simplify. So divide by 2, we have 4z squared. I won't think, oh, we cannot divide by 4 because this is 30. So you have 4z cubed minus 30z squared minus 15z minus 50 equals 0. This is the resolvent cubic. Its exact roots are complicated radicals. So they exist and are real, are complex exact numbers. But in practice, you can use numerical methods or CAS to approximate. I mean, you can use you can use Python, you can use any computational tool. So with one real root z not in hand, you can apply the difference of squares of square factorization step. So this shows how Ferrari's method proceeds in the general case when q is not equal to 0. So we will not carry the full radical simplifications there. It becomes algebraically heavy, but the algorithm structure is clear. So depressed quartic with p minus equals minus 15, q is minus 10, r is 24. The resolvent, you have resolvent cubic for z and use one real z to factor the quartic into two quadratics in y. So solve quadratics and then set x equals y. Simply b is 0 to get the four roots. For this particular quartic, we already know the four roots are x equals minus 3, minus 2, 1, and 4. from the factorization we started with. So I'm saying that even for this expression we started with, you don't even need Ferrari's method. But I'm just trying to introduce you to the idea. Okay. So the conceptual summary of worked examples. So you have x raised power minus 4 minus 10x squared plus 9 equals 0. Okay. So this was a depressed quartic with q equals 0. So it is faster to treat it as a quadratic in x squared. Ferrari's method still gives a resolvent cubic, but the simplification is unnecessary. So example 2, x raised power 4 minus 15x minus 10x plus 24 is 0. So this is a depressed quartic with p, q, and r all non-zero. So we formed the resolvent cubic, which is this. In practice, a computer algebra system helps to solve this cubic and carry out the resulting factorization. So this example illustrates the general Ferrari principle pipeline rather than aiming at manual radical simplification. So, like I said, it may be totally unnecessary, right, to use the Ferrari's method, but you need to understand, you just need to understand there's something called Ferrari's method, and it is particularly suited for solving quartic equations, that's polynomial equations in degree 3. So ultra compact Ferrari card now. So I mean, just a kind of run over the idea. So start with x raised power 4 plus bx cubed plus cx squared plus dx plus e equals 0. Then depress, set x to be y minus b over 4 to get y raised power 4 plus py squared plus qy plus r equals 0. Then resolvent cubic, you have 8z cubed plus 4pz squared plus 2pz minus q squared equals 0. Then pick a real root z, right? Y raised power 4 equals this, and expand into y squared plus p over 2 plus z squared minus 2zy. Factor into quadratics, then you solve them. So you have x, and then you now use x equals y minus b over 4 to get back what you need to get back. So we have some practice questions here. So we have conceptual questions. So why does Ferrari's method first eliminate the x cubed term from the quartic? I mean, we need to depress it, right? We need to depress the expression. In your own words, explain what a depressed quartic is. That is a quartic with the cubic term removed, basically. What role does a resolvent cubic display in the method? Do we remember what that is? I don't think I do remember. Okay, let's look at resolvent cubic. So that's why asking questions will help you to know if you really understood. So here, to make the identity in the previous cell valid, the parameter z must satisfy the resolvent cubic. So enforcing exact equality. So solving this resolvent cubic gives a value or values that allow the quartic to factor. So that resolvent cubic helps us to be able to factor into two quadratics. I want to believe that's a good answer to give for that. Okay, so what role does the resolvent cubic solve that? Explain why writing the quartic as a difference of squares helps to solve it. So when we express it that way, we can then equate it in. We can then solve two quadratic expressions and get our solution. Why is the q equals 0? No y term easier to solve than the general case. It is easier because you can solve it. You can, for instance, since you have depressed it by removing x cubed, you can then consider the rest of the expression as something in terms of x squared, which you can look at. That's a biquadratic, like I think it's called biquadratic. So you can see it as a quadratic term, which you get a value, so a set of values. You make a substitution, get a set of values, and then you substitute to now get the actual set of values using a quadratic formula. So we have some computational practice too. For each quartic below, do the following. If needed, divide by the leading coefficient to make it monic. Everything is already monic for all yeah, everything is monic already. Then depress the quartic by finding P, Q, and R. Then write down the resolvent cubic. Okay. You write down the resolvent cubic. Then for the simpler ones, you may solve directly by factoring or by viewing as a quadratic in x squared. Okay. So what I'm just going to do here is I'm going to take one of this. Okay. I mean, the general way to go, this it has been shown in 10. For x raised power 4 plus bx cubed plus cx squared plus dx plus z equals 0, write the formulas for p, q, and r again in terms of b, c, d, e. Write the resolvent cubic explicitly in terms of p and q. Describe how solving this cubic leads to two quadratics in y. So I'm just going to take that as I'll take a question and go as far as possible. I may not do it till the very end because I know anyone I take, I may be able to get an answer to it without even having to go through the Ferrari's method. So, let me take question 9. Question 9, we have x raised to power 4 plus 10x cubed plus 35x squared plus 50x plus 24. Using the Ferrari's method, right? Let's go. X raised to power 4 plus 10x cubed plus 35x squared plus 50x plus 24. So once you solve that using the Ferrari's method, okay. So I have to go back and forth. So to solve using the Ferrari's method, using the Ferrari's method. So we have x raised to power 4 plus 10x raised to power 3 plus 35x squared plus 50x plus 24 equals 0. Okay. So so like I said, I'll go back and forth to confirm. So the first thing we need to do is we want to write the formulas for PQR. Okay, of course, one thing we know already is that we can compare. So we compare with the standard, compare with the standard form, which is x raised to power 4 plus big B x cubed plus big C x squared plus big D x plus E equals 0. So we can do that much. And since we have that, we know that that can easily be set to be B is simply 10. B is 10. C is 35. C is 35. D is 50. D is 50 and E is 24. At least we know all this. So once we've stated all this now, let's go ahead and find PQ and R because we need PQ and R. So normally what I should be doing is to say X is equal to Y minus 10 over 4. Okay? Then I substitute that here. But that's not necessary. I can as well use the formula. If you do the whole thing, you get some formulas. Let's go and get these formulas. For instance, P is this P now. P is big C minus 3B squared over 8. Then Q is D minus big B and C, big C over 2 plus B3 over 8. And then R is E minus BD over 4 plus B squared C over 16 plus 3B raised to power 4 over 256. Now this is looking so big already, but let's see. We'll try what we can do. So D minus 3B squared over 8, yes. Then D minus, C. This is C minus 3B squared over 8. Q is D minus BC over 2 plus B cube over 8. Then R is E minus BD over 4 plus B squared C over 16. Then minus, okay, this is minus now. Minus 3B raised to power 4 over 256. I checked that again. E minus BD over 4 plus B squared C over 16 minus 3B raised to power 4 over 256. So, science can cause trouble. I know I've lost a math prize in high school because of my minus sign like that. So let's pay attention. That's why I like to cross-check these things before I proceed, because you don't want to go so far and then you discover you have made a mistake. So let's start with P. We want to compute P. P is C minus 3B squared over 8. So that means we have 35 minus 3 into 10 squared all over 8. So that is 35 minus 100. 10 squared is 100. That's 300 over 8. So, to avoid wasting time, I'll just go straight and punch the calculator for these things. I'll just save my time. I don't have to go through step by step. Okay, so we have 35. So this is 35 minus 300 over 8. 300 over 8. So that is minus 2.5. No, that's 150 over 4, 75 over 2. Right, 75 over 2. That's 7.5. So that makes sense. This is minus 2.5. Okay, that's P right there. So we need Q. So Q now is D minus BC. D minus BC over 2. Then plus B cube over 8. That is what Q is now. Okay, so let's go. So that means that Q is equal to D is 50. So we have 50 minus BC. B is 10, C is 35. So that's 10 into 35 all over 2. So this is 10 into 35 all over 2. b cube again. B cube now is 10. Okay, that is 10 cube all over 8. 10 cube over 8. Yeah. So like, again, I'm just going to punch my calculator straight for this, so I don't keep wasting time. So I have 50 minus 350 over 2. So that is 350. 350 divided by 2. Then plus 110, that's 1000 divided by 8. Okay. Oh, that's 0. Interesting. Q is 0. Wow. Okay. So we have 50, 350 divided by 2 plus 1000 over 8. That is simply 0. Interesting. Really. So this is 350 over 2. Okay. I hope everything is fine. So let me say this. This is. But why will it be 0? I'm wondering why it is 0. Shouldn't be 0. Why should it be 0? Um, okay, this is minus 0 minus that. Okay, minus 50. Okay. So this is minus 50 actually. Okay, so that works. So yeah, so this is simply 0. And since Q is 0, that makes life easy for us, right? Q is 0. So we know the next stage just works if Q is not 0. So Q is 0 already. So I think I'm already saying we don't have to worry ourselves. So, but let's still go for R. R is E minus BD over 4 plus B squared over B squared C over 16. Yeah. Minus B raised to power 4 minus 3b raised to power 4 over 256. So let me check. I mean, this one, I'm already feeling something may not be right. Let's go and look for R again. R, where is R now? R, yeah, R is E minus BD over 4 plus B squared C over 16 minus 3b squared over 256. That's it right here. So I come back here and try to compute that. So we have R to be, what is E now? E is 24. So we have 24 minus BD. What is BD? B is 10, D is 50. So 10 times 50, that's 10 times 50 all over 4 plus B squared C. B squared C, that is 10 squared 35. Okay. 10 squared times 35 over 16. Then plus 3b raised to power 4. That's 3 times 310 raised to power 4 minus 256. Okay, I'll just punch calculator for this also and just get the answer straight up. So here we have okay. So okay, that's 24 minus 500 over 4. That's 500 over 4 plus 100 times 5. That's 3,500. 3,500 over 16 plus 10 raised to power 4. That's 10,000 times 3. That's 30,000. 30,000 divided by 256. 30,000 divided by 256. So again, 24 minus 500 over 4 plus 3,500. This is minus. This is minus. So you see all the sign troubles. It's very important to pay attention to them. So 24 minus 500 over 4 plus 3,500 over 16 minus 30,000, yeah, over 256. So R is 0.5625. Okay, so we can approximate that to 0.56. So R is approximately 0.56. So I pick this now. So again, Q is 0. Thankfully, P is minus 2.5. So we have all that. Now that that is done, we go for the next step. Like I said, I just want to do it as much as possible. I've already seen that Q is 0, so I don't have to take it further. But I'll just try to get the resolvent cubic. Okay. The resolvent cubic is given as 8z cubed plus 4pz squared plus 2pz minus q squared equals 0. Okay. Um, so we can do that. So the resolvent cubic, the resolvent cubic is given as p of z, if you like, equals 8z cubed. Okay, let me even see. Is it an equation straight up? Uh, okay, it's an equation, so I can just go without the p of z. So it's something in terms of z, sha. So 8z cubed plus 4p z squared plus 2pz minus q squared equals 0. Okay, so this implies that we have 8z cubed plus 4. What is our p now? Our p is minus 2.5. P is minus 2.5 z squared plus 2 again, that's minus 2.5 z. Is it 2pz? Is it just 2pz or 2pqz? Let me see. 2, yeah, it's 2pz. Okay, that works. 2pz, so we are good. And then lastly, minus q squared. Q is 0 equals 0. So that's already something for us to ponder. So this implies that we have 8z squared. I mean 8z cubed. Then this is 4 times 2.5, that's 5. That's minus 10z squared. And this is minus 5z equals 0. So in this case now, we can then make that statement that since q is equal to 0, there's no point. There is no point trying to simplify, trying to simplify P of Z, which is the resolvent cubic. Okay, so that simply means that the original expression, uh, we can we're able to find better ways of solving the original expression. So I'm just going to stop on that note. I won't even bother. So we can find we can find easier ways. We can find ways of solving easier ways of solving the quartic equation. Quartic equation. Okay. So I'm just going to stop there. And we already know those ways. You can try to solve using factorization and things like that. You can already do that. Okay. So I'm going to stop on that note and feel free to try your hands on this on other of some of the other questions. And like I said, it's rare for you to need a Ferrari's method. That it's very difficult for you to get into a situation where the only solution method you have is Ferrari's method. It's very, very, very difficult because I mean you can always factorize, you can always try to make perfect square and then you have difference of two squares. Maybe I should even try that. I'm tempted to try that. Should I do that? I don't know. Should I do that? Should I not do that? Um, okay, I'm just going to leave it alone and let it be because I mean, you can always find other ways of solving your problems. So that'll be the end of this video. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay, if you have subscribed already, I thank you very much. If you haven't subscribed, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, and you see 3 levels of membership. At the highest level, one of the benefits you stand to gain, means other benefits at other levels, is that we can be able to hang out one-on-one if you're in the same geographical space at any point in time to discuss whatever interests you on my channel. If you cannot meet face-to-face, we can also hang out online, all right, to discuss anything that interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing maths right. I mean, this may be the last video on polynomial equations, except something else comes up. So till then, have a nice time. And I'm sure I think I'll be talking about lengths, areas, and volumes next. A whole playlist on that, talking about areas, volumes, perimeters, and things like that. Bye.